Alright everyone, this lesson is on complex numbers. Let's say that I had to simplify the square root of -4. We talked about in a previous section that you cannot take the square root of a negative number, and that is true because it's not a real number. It does not have a real number solution. But what I could do is this. I could write this as the square root of 4 times the square root of -1. I do know what the square root of 4 is. That's not a problem. That's just 2. The issue here is this, the square root of -1. And so what we do to deal with this problem is we actually just define the square root of -1 to be I. I'm going to write that up here. I is equal to the square root of -1. I, because this is called the imaginary, I is called the imaginary unit. I is the square root of -1. If I square both sides of that, then I get I squared equals -1. And so notice how strange this number I is. I square it and I actually get a negative number as opposed to a positive number. So the square root of -4 we can now say is the imaginary number 2i. There's actually lots of uses for imaginary numbers, even though the name suggests not. They're quite useful in electronics, and in our algebra class they are now going to allow us to solve equations that we couldn't have solved before. Let's try another one here. For instance, the square root of -25. I split that into two parts. That's the square root of 25 times the square root of -1. And that'll be 5. That's a 5 right there. And this, of course, is, we're just going to call it I. And so my answer is the imaginary number 5i. Now in general, what I can do is this. If I have the square root of -b, let's assume if b is positive to start with, and the square root of -b, I can split up into two radicals. I'm going to write that as the square root of b times the square root of -1. Well, that's the square root of b times I. It's customary to write the I in the front of a radical instead of the back, and so I'm going to write that as I square root b. And so I'll put that up here for another one of our little rules here that we have. If b is greater than or equal to 0, then the square root of -b is the imaginary number I square root b. Let's do a couple examples of using this rule right here. The square root of -16, using that rule, I could just write this as I square root positive 16. And so this is I times 4, or 4i. The square root of -7 is I square root 7, I square root positive 7. And, well, I can't simplify square root 7, so I guess I'm done with that one. So my answer is I square root 7. Square root -8. That's the imaginary number I square root positive 8. If you can simplify what's under the radical, you need to do that. Since 8 is 4 times 2, square root 8 simplifies to 2 square root 2. And so that, my answer is 2i square root 2. Let's try one more like that. Let's take, for example, the square root excuse me, of negative 18. That's I square root positive 18. Simplify the square root of 18. It's 9 times 2. Square root of 9 is 3. So we got I times 3 square root 2. My answer is the imaginary number 3i square root 2. Let's look at some examples now of multiplying with imaginary numbers. Multiply. The square root of negative 3 times the square root of negative 7. Now what I cannot do is this. I cannot multiply them directly as negative 3 times negative 7 and get positive 21. This is incorrect. Because this right here, when I went from here to here, I used the product rule for radicals, but the product rule for radicals does not work when both numbers under the radical are negative. It won't work. What I have to do is this instead. Since I know that these are imaginary numbers, I have to write them with i's first. This is I square root 3, and this is I square root 7. I now multiply them together. I've got I times I, so that's I squared. I can multiply the radicals together now because they're positive 3 and positive 7. So this is square root 21. But I don't leave it like this because, as we mentioned previously, I squared, put it right up here again, I squared is equal to negative 1. And so whenever you come across an I squared, you can replace it with a negative 1. Negative 1 square root 21. My answer is negative square root 21 here. Here's another one like that. The square root of negative 2 times the square root of negative 8. First we write those with i's. I square root 2, and this one is I square root positive 8. Multiply together. I times I is I squared, and then the radicals multiply to square root 16. Replace the I squared with negative 1, and the square root of 16 is exactly 4. So my answer here is negative 4. One more of these multiplication problems. Square root negative 5 times square root positive 6. Now there's only one imaginary number here, the square root of negative 5. This is I square root positive 5, and then square root 6 is just square root 6, it's a real number. So I only have one I here. So I'm going to have I, and then multiplying the radicals together, square root 30. And I can't simplify the square root of 30, so that's as far as this one goes. I squared 30 is my answer there. Okay, that's how we multiply imaginary numbers. Let's look at a couple division problems now. Square root negative 75 over square root negative 3. Always write them with i's first. So we got I square root positive 75 over I square root 3. Just like any other variable or a constant, if I have one in the numerator and in the denominator, they will cancel away, so that's gone. I'm left with square root 75 over square root 3. I can use the quotient rule to simplify this further. This is the square root of 75 thirds now. 75 divided by 3 is exactly 25. And so my answer here is just a positive 5. And let's look at this one, square root negative 32 over the square root of 8. I have an imaginary number in the numerator. That's I square root positive 32 over square root 8. Here the I doesn't cancel away with anything, so I have to leave it there. These two radicals, I can now use the quotient rule and write that as the square root of 32 over 8. But 32 over 8 is just a 4, so we've got I square root 4 now. Square root of 4 is 2, and so my answer here is the imaginary number 2I. And we've divided our imaginary number. Okay, now that we talked about the imaginary number I, what is a complex number? If A and B are real numbers, then A plus BI is a complex number. So anything of the form A plus BI is considered a complex number. Some examples of complex numbers. Five plus 2I is a complex number. The 5 is the A. That's called the real part because it doesn't have an I on it. And the 2 is called the imaginary part because it's the part that is multiplied to the I. So other examples of complex numbers would be 1 minus 4I, 1/2 plus 1/3 I. You could even have a 0 in the front, 0 plus 2I. You could have a 0 in the back. You could have 7 plus 0I, 0.2 plus 0.3I. Various different complex numbers we could come up with here. Note this, though. If A equals 0 and B is not 0, then we have what are called pure imaginary numbers. This is a W here. For example, if the A is 0, then the real part is missing. Remember that this is the real part, and this is the imaginary part. So if I make A 0, then I get numbers such as 5I, 2I, negative 1/3 I, maybe just negative I. Those are all considered pure imaginary numbers because the real part is 0. If, on the other hand, B equals 0 instead, then we have just real numbers. For example, if the B is 0, something like 5 plus 0I, well, that's just 5. So that's just a real number. Or 1/2 plus 0I, well, that's just the number 1/2. So putting all this together, we've got complex numbers, A plus BI. Complex numbers can be broken up into two categories: real numbers, where the B is 0. There's still A plus BI, but the B part is 0. And pure imaginary numbers. They're a plus bi, but the a is 0. And so you put all your real numbers together and you put your pure imaginary numbers together and you get what are called the complex numbers. These are the real numbers that we've been dealing with throughout the book, and we talked about in a very early chapter, probably chapter 1, real numbers could even be split up among the rationals and the irrationals. And then even the rationals can be divided up among integers and non-integers and numbers like that. Okay, so as far as mathematicians are concerned, complex numbers comprise basically every number that you can think of. Adding complex numbers is very simple. For instance, 2 plus 3i is a complex number, and I want to add that to 6 minus 4i, another complex number. Very simple. All I got to do is add my like terms. 2 plus 6 gives me 8, and the 3i minus the 4i is negative 1i. And so adding those complex numbers together, I get 8 minus I. Subtracting is basically the same. Subtract. Let's say we have the complex number 6 plus 5i, and we want to subtract 3 minus I. We just have to remember to distribute the negative sign. So we've got 6 plus 5i minus 3, and then this one over here will become a plus I. Combining your like terms, we will have 6 minus 3, that's 3, and then we've got 5i plus an I, that gives me 6i, 3 plus 6i. Now let's do one more subtraction. Negative 9 plus 4i minus negative 9 plus 8i. When subtracting complex numbers, once again, you got to remember to distribute the negative sign. So this will be negative 9 plus 4i. This will be plus 9, and this will be minus 8i. Adding your like terms together, those numbers are, that's 0. And then we got this and this, which is negative 4i. And so this turned out to be a pure imaginary number, negative 4i. That's how we add and subtract complex numbers. Let's now look at multiplication. 6i times 4 plus 3i. This is just the distributive property, so not really anything new to us. Let's distribute. 6i times 4 is 24i, and then 6i times 3i is 18i squared. Remember that you treat this I just like a variable when multiplying, dividing, adding, and subtracting. Now we're not going to leave it like this because we know that I squared is equal to negative 1. So we always replace the I squared with negative 1 when we see it. That's 18 times negative 1. And so my answer as a complex number, put the real part in the front, negative 18 plus 24i. And we've multiplied it. Here's another one, 3 plus 2i, 5 minus I, multiplied together. Well, as you may guess, I'm just going to use the FOIL method here. to multiply these complex numbers together. So let's see what we have here. 3 times 5 is 15. That's going to be minus 3 times I. That's plus 10I. And then multiplying the last ones together, that is negative 2I squared. I've got 15. Combine these like terms in here. That's going to be 7I. And then on the end, remember that I squared is negative 1. And so this is negative 2 times negative 1. Negative 2 times negative 1 is a positive 2. So I can add the real numbers together here. The 15 and the 2 are combined to give me 17 plus 7I. And we've multiplied the numbers together. Let's look at another one where we're multiplying here. Three minus 2I times 3 plus 2I. Notice it looks like a difference of squares pattern, but I'm still just going to FOIL it out. Let's see what we get. 3 times 3 is 9. That's going to be 6I. This times this is negative 6I. And then finally we've got a negative 2I times a positive 2I. That's minus, not plus, it's minus 4I squared. With the difference of squares pattern, the two middle terms always cancel out, and they do here. And so now I have 9 minus 4I squared. But remember, we never leave the I squared there. We always replace it with negative 1. So we've got now 9 minus 4 times negative 1, which is going to give me 9 plus 4. My answer is just the real number, 13. All the i's canceled there. Right, that is how we multiply complex numbers. Now let's look at some division problems. Let's do this one first. 8 plus 9i over 5 plus 2i. Now when you divide complex numbers, you want to multiply top and bottom, numerator and denominator, by the conjugate. And we've talked about this in a previous section. I'm going to multiply this complex number by the conjugate of the denominator. You always multiply by the conjugate of the denominator. And the conjugate of 5 plus 2i is just 5 minus 2i, top and bottom. So notice I'm really just multiplying by something equivalent to 1. I've got to FOIL this out. So I'll take the numerator first. FOILed out, 8 times 5 is 40. 8 times negative 2i is negative 16i. 9i times 5 is 45i. And then we've got 9i times negative 2i. That's negative 18i squared. So the numerator FOILed out is that. The denominator FOILed out. This is a difference of squares. The two middle terms cancel, so what I don't even write those out. I just multiply the first ones together. 5 times 5 is 25, minus, it's my difference of squares pattern, 2i times negative 2i gives me a negative 4i squared. Oh, I'm sorry. Put two negatives in there. Let me back up. 2i times negative 2i is negative 4i squared. There we go. That's better. Okay, combining our like terms up here, that will give me 40 plus 29i. I squared right here I would replace with negative 1, and so this is minus 18 times negative 1 all over. 25 minus 4 times, replace this I squared also with a negative 1. Now going up here. This is an 18 plus this 40 gives me 58 plus 29i in the numerator. In the denominator, I've got 25 plus a 4, which is 29. Almost done here. I can reduce a little bit. With complex numbers, the best approach is to split the fraction into two parts. Notice I'm putting the 29, the denominator 29 under each part, and then simplify each fraction individually. 58 over 29 is exactly 2 plus 29 over 29 reduces to just this I here. So my answer is 2 plus I. Let's look at another problem similar to this. Two plus I divided by 3 minus I. So once again, we're going to multiply by the conjugate of the denominator. Multiplying by the conjugate, I've got to FOIL all this out. Let's see what we have in the numerator here. 2 times 3 is 6. Plus 2i, plus 3i, plus I squared. In the denominator, difference of squares pattern. 3 times 3, 9, and negative I times positive I minus I squared. Okay, we've got it all multiplied out. Combining our like terms right here, 6 plus 5i plus I squared, remember that's really a negative 1, so that's minus 1 here. 9 minus, that also is going to be replaced with a negative 1. So we got 9 minus a negative 1. And so we end up with 6 minus 1 is 5 plus 5i in the numerator. The denominator is 10. To simplify a little further, put the 10 under each term in the numerator. So I'm going to split this up as 5 over 10 plus 5i over 10. Reduce the fractions, and we have our answer, 1/2 plus 1/2 I. And it's done. It's divided. Notice it's in the form a plus bi. The a is 1/2, and this b is the other 1/2. Let's do one more similar to that. 5 over 3 minus 2i. So once again, I'm going to multiply the top and the bottom by the conjugate. Three plus 2i over 3 plus 2i. In the numerator, I'm going to distribute. 5 times 3 is 15, plus 5 times 2i is 10i. For the denominators, that's my difference of squares pattern, so the middle terms cancel. 3 times 3 is 9, and then minus 2i times 2i is minus 4i squared. I'm going to leave the numerator as it is. That's 15 plus 10i in the numerator. the denominator, 9 minus 4 times this I squared right here can be replaced with negative 1. And so I've got 15 plus 10I over, how much is that going to add up to? 9 plus 4, so that's 13. So I got 15 plus 10I all over 13. To write that as a complex number, we split that into two fractions. My answer is going to be 15 over 13 plus 10 over 13I. And now it's in that form, A plus BI, the complex number form. Now this one looks a little bit different, but the process is the same. One plus I divided by I. We're still going to multiply by the conjugate. It's not considered simplified if there's still an I in the denominator. No I's can be in the denominator. So we've got to get it out of there. Now the conjugate of just I, let me give it apostrophe. The conjugate of I is just negative I. So I got to multiply this by the conjugate, negative I over negative I. Let's see what we get if we do that. Distributing in the numerator, 1 times negative I is negative I. Negative I times a positive I is negative I squared. And in the denominator, negative I squared. Now remember our I squareds, the negative I have to leave alone, but the I squareds can be replaced with negative 1. So that right there is a negative 1. And this right here, notice the negative sign's on the outside, so I got a negative, negative 1. Putting my answer up here, negative I plus 1 over 1. And so my answer is just 1 minus I. Okay. And we have divided our complex numbers. One last thing on complex numbers, and that is this. Let's take a look at this pattern. We have I squared we know is negative 1. I cubed. What would I cubed be? Well, I could write I cubed as I squared times I. I squared is negative 1, and so this is negative 1 times I, which simplifies to negative I. So I cubed is equal to negative I. You can do the same thing with I to the 4th. I to the 4th can be written as I squared times I squared, but that's just going to be a negative 1 times a negative 1, and that will just be positive 1. So I to the 4th simplifies to positive 1. We'll try I to the 5th and I to the 6th here. I to the 5th power. One way to write that is I squared times I squared times I. But that's a negative 1 times another negative 1, and that's just I, so I have to leave it as an I. And that's a positive I. So I to the 5th simplifies to positive I. I to the 6th, that's I squared times I squared times I squared, which is a negative 1 times a negative 1 times a negative 1, which is negative 1. If I try I to the 7th, another way I could go about this is I could write that as I to the 6th times I, but we just found out that I to the 6th right here is negative 1. So this is a negative 1I, negative I. And then lastly, I to the 8th. one way to write I to the 8th is I to the 4th times I to the 4th. But if you look back at our pattern, I to the 4th way up here is just 1. And so we've got 1 times 1, which is just 1. Now there's actually a pattern to this. The pattern is, it goes I, negative 1, negative I, 1, and then it repeats the pattern. I, negative 1, negative I, 1. And so if I were to keep going, I to the 9th would be I to the 10th would be negative 1, I to the 11th would be negative I, and I to the 12th would be 1. Keeps repeating this pattern. I, negative 1, negative I, 1. Note which ones are equal to positive 1. I to the 4th, I to the 8th, I to the 12th. The next one would be I to the 16th. All of these will equal positive 1. What do they have in common? I raised to a multiple of 4. They all equal 1. I can use this fact to simplify. For example, if I have I to the 21st power, I'm going to write that, or I'm going to break it up so that I have a multiple of 4. That's I to the 20th times I to the 1st. But from what we just talked about, since 20 is a multiple of 4, that has to equal 1. And so this simplifies to just I. I to the 50th power. Nearest multiple of 4, 48. It's I to the 48 times an I squared. Since 48 is a multiple of 4, I know that this is equal to 1 in that pattern that we developed. So that's I squared, but we know I squared is negative 1, so this reduces to negative 1. I to the 39th power. I can write that as a multiple of 4, I to the 36, and that would be times an I cubed. I to the 36 is equal to a positive 1. So we've got this simplified to I cubed. And I cubed can be simplified even further. It's I squared times I. Since I squared is negative 1, we'll have a negative 1I. The answer is negative I. And last example. What do we do if we have, for instance, I to the negative 9? Well, we have to remember what a negative exponent means. I have to flip over the number. So this is equal to 1 over I to the positive 9. Now, I to the positive 9, let's see if I can write that as something with multiples of 4 in it. Well, that'd be I to the 8th times I. From our pattern, since 8 is a multiple of 4, I know that I to the 8th is a positive 1. So this just becomes 1 over I. It's still not considered simplified because you have a I in the denominator, so referring back to what we did earlier, we got to multiply this now by the conjugate, negative I over negative I. Negative I is in the numerator. In the denominator, I have negative I squared. So we'll have a negative I over a negative 1. I've replaced the I squared there with a negative 1. And so this simplifies to just negative I. And there you have it, our lesson on complex numbers.